Yeah. So weathering and sedimentary processes, you can kind of think of it as like you would in chemistry. You've got some reactants, like you're going to react two chemicals together, two chemical compounds, and you dissolve them in water, and maybe you have calcium ions and sulfate ions or chloride, something like that, and you're going to precipitate something, and maybe you're going to precipitate some kind of weird salt or anything or something like that, and that's the product of the reaction. In the real world, we start with something like we have here with this piece of granite, and you can see, we talked about this last week, you can see the gray glassy quartz and the pinkish feldspar, potassium feldspar, and then there's white, probably sodium rich plagioclase feldspar, and then the black is biotite mostly, so black mica. So we start with that assemblage of minerals, and that would roughly represent the composition of the continents. Like if you took all the continental crust and melted it and gave it a bit of a stir, it would have a composition very similar to granite, like that piece. This is a piece of granite countertop that we've got. So let's start with that. And so we're going to start with a material like that. And so we'll start with granite. Don't take it for granted. It's a cool rock. And we're going to go to a sedimentary product that is sediment, soil, potentially. And we start out with the number one mineral typically in a granite, maybe not this particular example that I just put up there with it, but something like potassium feldspar. So the chemical symbol for potassium is K. You know, you have some weird, that's a D, feldspar. When you have weird chemical symbols for elements, you know, almost certainly they were known in ancient times. And so the ancient word for potassium was casium with a K. And, you know, like sodium, chemical symbol for sodium is like Na, and it's not So or something like that, because sodium was known by the ancient Greeks, and the ancient Greek word for sodium was natrium, so Na for sodium. Okay, and so you have potassium feldspar, and you've got stuff like potassium, of course. If I ask you what's in potassium feldspar, you better have potassium down. Aluminum, it's an aluminosilicate, that's very important. Silicon, and oxygen. Okay, and you don't have to memorize this or anything, but there's 3 of those and 8 of those and 1 potassium, 1 aluminum. So one thing that you notice is there's no water, there's no iron, and it's a pretty simple mineral, relatively speaking. Chemically, it is. And then what happens when you weather that and you produce an alteration of this, the aluminum is very insoluble in the feldspar. So aluminum is extremely hard to get into solution. You need high temperature and or low pH acid solution. And aluminum is weird. You might have learned in chemistry, aluminum is weird because it'll dissolve in a very, very alkaline or basic solution. So extremely high pH. So pH of 10 and above, or pH of 2 and below, and you can move aluminum. You can dissolve it. You can dissolve an aluminum can, like a beer can or a Coke can, in a strong acid or an extremely strong base solution. Or just heat it up really hot and it'll react. There will be blood. And you make, because of aluminum, you make clay minerals. Okay. So the aluminum is so insoluble, there's going to be a solid product left. And Boggs, in that first chapter, when he talks about weathering and weathering reactions, he said the dissolution of feldspar and other minerals like that that have aluminum, it's an incongruent dissolution, which means there's a solid product left. And the solid product is the clay minerals. It could be one clay mineral, like kaolinite, or it could be multiple clay minerals, depending on what's going on. The other thing that gets left also in the water then is potassium. So potassium ions go in the water, and that goes to the oceans. The number 2 mineral in granite and kind of defines granite is quartz. What's in quartz? Not much. Silicon and oxygen. Silicon and 2 oxygens. Silicon dioxide. Very simple chemical formula. Silicon dioxide. Silicon is very reactive. It has it'll give up, or it needs 4 electrons, and it tries to get those from oxygen. Get some? No. Oxygen takes the electrons from silicon. What am I saying? Damn it. Because oxygen wants electrons really, really badly. I mean, it'll rip electrons off your grandmother's nose. It'll rip electrons off your grandmother's kitten while she's holding it. So oxygen's really aggressive. It wants electrons, and it pulls 4 electrons off of silicon and in that structure. Okay, so it's really going after the oxygen or the electrons in the silicon atom. And so what do you make when you weather quartz? Smaller quartz. Of course. You dissolve a little tiny bit, like a few parts per million. And there's silicon like in the Fox River, and it's floating around as silica, but as an acid. So it's H4SiO4, uncharged. Silicic acid. So that's the dissolved form of quartz, basically, is silicic acid. And all silicate minerals will break down a little tiny bit and release some silicic acid. It's an acid, so it dissociates, and that probably, but it doesn't like to dissociate very much. And the most common in like the Fox River by a little bit is H3SiO4, and with a minus. So that's what's in the Fox River mostly. Some of it is undissociated silicic acid, H4, but some is. And then another mineral, maybe Plagioclase Feldspar. And typically, in this case, and in the case of granite, it's sodium rich, Na, and aluminum, and silicon, and oxygen. And it can have that kind of a formula. If you start substituting calcium for the sodium, the charge, the oxygen, the balance has to change a little bit, and the number's a little bit different, but that's not important. Plagioclase feldspar, the other big component of granite, is going to have sodium in the case of granite, and as you go to more mafic rocks like basalt, you substitute calcium instead of the sodium. Okay, so sodium, aluminum, silicon, and oxygen. And what's going to happen when it falls apart at low temperature in the presence of water? Clay minerals, because of the aluminum. Anytime you have the aluminum there, you're going to make clay minerals. And, you know, we could make some sodium in solution that goes to the oceans and makes it salty. Okay, and then we have a black mineral, biotite, black mica. And it's got potassium. Man, there's a lot of potassium around, isn't there? Iron, magnesium, aluminum, silicon, and oxygen. But the one other thing we have to throw in here is water in the form of OH, as an OH radical. We'll put a 4 there. Okay, so black mica, biotite, potassium, iron, magnesium, aluminum, silica with water in the structure. So this is where the action happens, because the iron here is iron plus 2. This is plus 2, plus 1. Iron plus 2 is not stable at the Earth's surface in the presence of oxygen and water. And so it tries to oxidize. An electron comes off. Somebody grabs onto an electron. Guess who that somebody is? Yeah, it's a real nasty guy. Oxygen rips an electron off of iron and makes it plus 3. And iron plus 3 is actually smaller than iron plus 2. It falls apart and it makes that stuff that's forming on my car right now. Iron hydroxide, rust. That's rust. And so it's first tied to water, to OH. It will clean itself up over time and become nicely crystalline and make iron oxide. But for now, the water's in there. It's going to release some potassium again, some magnesium, not iron. Iron's going to precipitate as rust. And we are also not going to let the clay mineral go, because there's, look at that, aluminum. So we need a clay mineral in here too. Now, probably it's going to be a different clay mineral than forms when feldspar weathers, because there's magnesium and iron around. And so typically this clay mineral will be different. It might be a green clay mineral called chlorite. And we'll talk about those later, so don't worry about that. Yeah, I don't know if I can focus this little guy. Maybe a little bit. Yeah, so you know, probably chlorite, because it's going to have magnesium and iron in it. And this guy could be a potassium-bearing clay mineral, or it could just be kaolinite, which doesn't have anything like potassium or sodium. And this guy probably is going to be a sodium or calcium-bearing clay mineral. So there's going to be a little bit of difference. Now, there you go. Granite breaks down. Let's see some broken down granite. Everybody loves broken down granite. So here's fresh granite this is from Colorado. It's Flagstaff Mountain west of Boulder, Colorado. And you can kind of see what's going on here. You see Plagioclase Feldspar, Potassium Feldspar in pink, gray glassy quartz around, and black zones of biotite, black mica. And what happens is, first, the biotite, of course, rusts. So the biotite starts breaking down and releasing rust. That's iron hydroxide. And it's just like rust that you would find in metal, like your car or something like that, or my car. That rust will become red through time, and it'll become hematite as it crystallizes and cleans itself up. But there's what the granite looks like in the soil zone. So the plants and the weathering, the water and oxygen are really doing a number on it. So the granite is falling apart. And if we look at it up close, it looks like it's, you know, it looks like it's, you could, some of this you could probably break up with your hands, like this piece here with the edge. You might be able to break that, and certainly with a hammer, it would just fall to pieces if you hit it with a hammer. And so if you look at it up close, there's what the rock looks like up close. The biotite is falling apart, and that loosens everything up. And then also feldspar is altering to clay. You can see how it's looking chalky. And then the sediment around it that's coming off that granite is feldspar rich and quartz. So it's got some unaltered feldspar. It's got quartz, and I guess the other thing that's going to be in this mess is clay minerals. Okay, so, and you know, the plants are integral to this process. The plants are taking this rock apart chemically and mechanically, and we'll talk about that. Here's an example of granite in a desert. This is in Western Australia, in an area that I worked in, and believe it or not, this is a granite exposure of granite. It's got all kinds of fractures that make it look like sedimentary rock. And when I saw it from a distance and started walking up, I thought, well, this is some type of weird old sedimentary rock. And I couldn't really tell what it was until I really looked at it closely and started banging on it with my hammer and got something that's kind of relatively fresh to actually see. But this is granite in a desert in Western Australia. It would never, ever weather like this in this kind of climate in a desert. This is weathering that occurred back 50 million years ago and before, when the climate in Australia, just like in North America, was much, much more humid and tropical. The cool thing is, like walking around this, you'd never know what you find in these caves, these openings in the rock. A weird thing about, like, a little creepy, but kangaroos like to find places like ledges and caves and stuff when they're sick and they're dying and they're old and dying. It's kind of it's a really weird thing. Like, I've climbed into some caves and stuff in this part of Australia, especially, and there's just bones everywhere. And so I walked around here, and there's a kangaroo that died. It's very dehydrated. Hang on a minute. Sorry, I had a sneeze. So here's a very dehydrated kangaroo. I don't know how long it died, how long ago, years ago. The dingoes will get in here, and then there's some also like buzzard birds and things will get in here and kind of consume them. But it's so weird to climb up a ledge or something and climb over the ledge and you see all these bones. It's really creepy. But also on the walls here, there were like rock art, lithographs, petroglyphs, and this style with like just a hand print is the oldest style rock art in Australia, and it probably dates from more than 20,000 years ago. So it's pretty cool. I'll have to show you some more of the art from different parts of the country. Like, there's 16th century and 17th century sailing ships, and there's all kinds of things like you find in these caves and ledges and protected areas. But this is some of the oldest rock art. So people came from Indochina region across Indonesia during the last ice age 40,000 years ago, and like the maximum of the ice age from 40 to 20,000 years ago, you could pretty much just walk and then a short canoe ride to get to Australia. It wasn't very far. And so that's when the first colonizers came to Australia, first Aboriginal people. But so let's think about this. If we took this material and we changed the composition, because on the field trip, people were finding black, grungy rock, and some people were like smashing it with their hands. It was so altered. And so here's a piece of the mantle, this green rock. It's called peridotite or peridotite. And peridotite is olivine. So it's basically olivine rock. Olivine is olive green, right? And God, I can't remember what's in it. I think it's iron, magnesium, no aluminum, and silicon. So iron, magnesium, silicon. It's a pretty simple composition, and the key thing here with this mineral, this green, beautiful mineral, is these little building blocks are not stuck together. There's either iron or magnesium between each one of these little pyramids, these little Lego building blocks. And so the mineral comes apart really easily. And those geologists on the left there are standing on rock almost similar to this composition. It's more like the black rock here. That black is basalt. That's what the ocean crust is made out of. So the black is basalt here. And so what do we have in basalt? Olivine? Maybe. God, I can't remember. Is olivine, olivine, or olivine with an E? I guess if it's in green, it's got an E, and if it's in black, it's got an I. I think that's, yeah, if it's in basalt, it's got an I. What was the other thing? Yeah, so this is minor. This is number 3. Taryn says it makes sense. That would be number 3. Number 1 would be calcium-rich plagioclase feldspar. Feldspar. And then, so this would be number 1. I'm doing this backwards. Why am I doing this all mixed up? It's life. Pyroxene. Pyroxene is a pyroxene's a family. Most common one is augite. Augite. So pyroxene is a family of minerals, and really calcium plagioclase is too. Sodium calcium plagioclase. It's kind of a family of minerals, and augite is the most common. But this would be number 1, number 2, and olivine is number 3. It might not be there at all in a basalt, but it's usually there at least in a little bit low concentration. So calcium, aluminum, silica, iron, magnesium, calcium, aluminum, silica, no water, all anhydrous. And then olivine is iron, magnesium, and silica. And the key ingredient there is the iron. Look at the rocks that those guys are standing on. Rusty as heck and all worn down. That is basically the same rock that I think Bella handed me that was falling apart. It was black and kind of, in that case, it was kind of glittery because you could still see cleavage planes in the Plagioclase Feldspar. In this case, this has been through probably Mesozoic, really intense weathering. And so it was exposed to a lot of rain and warm weather. And so it was really dissolved and altered and rusty. But it's a rusty mess. This is a guy that I work with in Canada, Pierre, He's at Queen's University now, and Franco is an Italian Australian, which is fairly common. And then this is Sarah Aiken from Wild Rose, Wisconsin. So she did her undergrad at UW Oshkosh, and she was a really good student and everything. She went to field camp in Utah, and then from field camp in Salt Lake, she flew to Perth and met Pierre and I. We'd been there for a couple of weeks working, and she did her master's project on rocks in this area on iron formation. So we got to work in the desert for a couple of weeks doing field work and hanging out. So it was really, really kind of a good time and good experience for her. She loved Australia so much. She married an Australian and moved back to Australia. She lives in Melbourne now and works for Exxon. But here's what the rock looked like. And this looks a little bit like the sample that I think it was Bella brought me that was kind of falling apart. And you see the rust and the green color. Remember the green color? We saw that in that sample on Saturday. And the green color is that kind of this drab, waxy green. That's not the olivine, the mineral. That's an alteration product. That's chlorite. It's a clay mineral. And it's forming as especially the pyroxene falls apart. Yeah, it just kind of fell apart, and you kind of wanted to bring it back, but if you put it in your backpack after about a half an hour, you'd have a pile of black, grungy, gravelly sand. But you see rust and chlorite forming, so it's coming apart. Yeah, it was a sad day, definitely. But here's what that rock looks like up close. So that's the gabbro sitting there in the desert, and you could just pick this up with your hands and break it up, and it weathers round like this, and that's a key important thing to keep in mind. If you weather in place and let it essentially dissolve, it'll produce rounded corners and particles. It doesn't have to be transported very much. We see this phenomenon out west in the Rockies. You'll go and you'll see like a giant boulder like the size of a minivan sitting down in a canyon, and it's not round and spherical, but it's a little bit rounded, right? The corners are rounded off, and people look at that and they say, wow, there must have been a heck of a lot of water in this stream to transport that boulder the size of a minivan. And actually it fell from a canyon wall where it was sitting up there weathering, and all the corners had been dissolved off. It fell and probably hasn't moved ever since. And so you kind of have to be careful. Like, I've seen lots of geologists look at stuff like that and say, whoa, there must have been like really big floods in the past that moved this giant boulder. And no, it went into the canyon rounded like this thing did. This hasn't moved, and it's rounded. And you can pick that up and just crush it in your hand. But here's one of our campsites. So we just camped out in the desert and for like 2 weeks and did field work. And pretty much every day we picked up and drove somewhere. These are special vehicles they're from the Western Australia Geological Survey, and they've got emergency water tanks underneath them. And we'd always stop and fill up with water, even though we were there in the winter. So this was like July, and so the daytime temperatures was really comfortable, like in the 80s, and at night it was quite cool and clear. But in their summer, it's 120 degrees during the day, and people die all the time. Like, if your car breaks down, you're not supposed to leave your car, and you're always supposed to have emergency water. People will get out of their car and start walking because they think, oh, I saw a farmhouse, like, 1 or 2 miles back on the road. It's not very far, and they start walking, and they end up getting so hot and dehydrated they die before they get there. It's kind of like analogous to if you get stuck in a really bad blizzard in Wisconsin, in the winter, you're supposed to stay in your car and not go hiking out, because you're safer actually in your car. But yeah, so really cool, cool trucks. Really, they're actually very expensive. Turbocharged diesel and water tanks and all kinds of extra gear for working in the country. Sedimentary basins. So let's think about sedimentary basins. A sedimentary basin is where we store sediment. So it's a topographically low area that receives and accumulates sediment. And let's see. Yeah, so I often will make like a cartoon diagram of what a sedimentary basin looks like. And it's like this whole big area that's, you've got mountains and hills and streams running into a low area. You might have a lake or the ocean, and sediments accumulate. And you can accumulate sediments in a sedimentary basin until you kind of fill up to some kind of erosional base level. And the ultimate, on a global scale, the ultimate base level is sea level. So you can pile up sediment in the oceans basically until you get to sea level. There's a few exceptions, like wind-blown sand dunes along the edge or a volcano, but that's not sediment. But you can make a volcano and then pile up sediment on an island for sure. But the ultimate base level is sea level. So any island like Hawaii is going to build up, and it erodes and weathers. If you stop the volcano, which is what happens with the old islands as they move off the hotspot, they erode and weather down to sea level, and then the ocean crust cools further and they subside, so they basically sink. And there's a whole trail of old Hawaii volcanoes going off to the northwest away from Hawaii. So so we study sedimentary basins because if you have faults, like big regional faults, often warm groundwater will get in these faults and heat up and circulate like a convection cell. And then that warm water often is chemically reactive, either because it has lots of cations or it's interacted with some type of rock that's maybe made it acidic or basic. And it can carry things like gold and carry other metal deposits. Copper is a good one. We can get flow within the basin, and that flow can interact with fault zones and make all kinds of major metal and economic deposits that we depend on. And you can get flow near the surface, like with groundwater. So we study sedimentary basins for a lot of different reasons: for groundwater, for petroleum, for metal deposits, copper, even iron, gold, all kinds of things. And so sedimentary basins look different. There's a lot of different variety. This is kind of a classic basin shape. And so this is up above the tree line. So get rid of that pesky vegetation, right? And you can see all the rock layers here and sediment being shed into a valley. And then there's a modern stream reworking those sediments and putting down layers of sediment through time. And often the layers of sediment will build up slowly and cause the crust to subside. And so they build up and then the crust sinks very slowly, and you can keep this kind of equilibrium where sediment's introduced and keeps building up a thickness. And I showed you this photo last week when we were talking about types of bedding. And I pointed out the cross section of a river channel here, and then most of these more continuous river sands are longitudinal cuts through the river. You see this one kind of comes and goes and then disappears. So the river curved and migrated off of this plain, this exact area, and so it just seems like it disappears. These red zones are soils. So I made the equivalence the other day. This is the soil, and then along these trees, the modern day stream is down there. It's a small river in western Wyoming, and you have, so the gray sands are being deposited in the channel, and then this vegetated floodplain is producing all these finer grain red muddy sediments, and they're not red at first. They look like those weathered rocks in Western Australia. They're brown, and it's actually iron hydroxide, not hematite. But if you take that iron hydroxide, and especially if you can raise the temperature a little bit through burial, so you bury it a kilometer or two and raise the temperature a little bit because of the geothermal gradient, and give it time, just like a fine wine, it gets better with age, and it crystallizes, kicks off the water, and you have hematite. So hematite doesn't form at the Earth's surface. It takes a lot of time, and preferably a little bit of raised temperature, to clean up that messy crystal structure and make this red color. This was originally tan brown, these red layers, when they're deposited. And if you've seen construction, right? You see a trench or something, you see that brownish layer below the topsoil, that will turn red, this color, give it 20 million years or so, and it's going to be nice red color like this. Okay, it starts out tan brown, but it turns red. And then, like, the ultimate sedimentary basins are the ocean basins. So you could say the North Atlantic is a sedimentary basin, or you could say this western part of the North Atlantic is a sedimentary basin. The Gulf of Mexico is a sedimentary basin. So these are like the ultimate large scale, big scale sedimentary basins. These are different because they're underlain by ocean crust. So we have continental crust and ocean crust. And ocean crust is, as you learned in kindergarten in first year geology, ocean crust is made of basalt. It's heavy. It has more iron in it, more calcium, so it makes it heavier than the continents. And so it rides lower in the upper mantle. And so the average depth of the ocean basins is about 4 kilometers. So if you take all these bars, not the kind of bars you're thinking of, but all these histogram bars, and average them out, it's about 4 kilometers deep. And continental crust is made of granite, and those minerals are lighter than the minerals that make up basalt. And so they float higher in the upper mantle, and you have a buildup of thicker material on the continents because they're floating like wood in water. And you have the average elevation of the continents at just under a kilometer. It's about 700 meters above sea level. So here's sea level. And so most of the land on Earth is within a kilometer of sea level, and only rare little bits are high mountains. They're pushed out of equilibrium floating in the upper mantle. And then ocean crust is mostly riding, that's the equilibrium point for ocean crust. Some of it's pushed out of equilibrium much deeper by plate tectonics. Okay, so these are the ocean trenches right here, like the Marianas Trench over by the Philippines, and the little trench right here, the Cayman Trench in the Caribbean. Those are pushed out of equilibrium because they're two plates running together, and they're pushed down. And these are out of equilibrium because they're two plates pushed together, and they're rising up in the continents. Okay, so the ultimate ocean base, or the ultimate sedimentary basin, is the ocean basins. So let's think about how these processes work in a sedimentary basin. And we take these reactants and products, and they start out like that granite in Boulder, Colorado, in the mountains. It's granite, and then right next to it is soil. So you have the parent material, which is the rock that's weathered, and it alters and makes a soil. You could say, in that case, sediment sitting around on the soil, but it's a soil. So we have physical and chemical processes doing that. Physical processes include freezing in the winter and expanding ice, but it also includes the plants. The plants are breaking up the rock. And then I showed you some of the chemical results of chemical processes. So rust is a chemical product, iron hydroxide. So then we take that material from that mountain in Boulder, and every time it rains, a little bit of it washes down the mountainside. So we get erosion. It goes down into streams, and there at the bottom of that mountain, there's a stream called Boulder Creek, and it gets transported now down the stream. So we're gonna take this material, this box in this flowchart scheme. We're gonna take reactants and make products, and now we're gonna act on them, and we're gonna erode them and transport them. And so that erosion and transport means smaller particles. It means more uniform sizes the longer it's transported. And it means more rounded particles. So the rounding improves. And chemically, the composition of that material is becoming more and more stable at the Earth's surface, right? That soil, if you put it back in the mantle, is really unhappy. It would make all kinds of new minerals out of the soil. If you put it in 1500 degrees C and under a great deal of pressure, you're going to make metamorphic rocks, essentially. And you're going to make a magma, and then if you cool it, you could make some weird composition igneous rock from it. So it's happy at low pressure, low temperature, in the presence of oxygen and water. But the basalt and the olivine and the biotite and all those minerals that formed in igneous rocks are extremely unhappy at the Earth's surface. They break down. Okay, so in this case, we've got stream processes doing this mostly. Not 100%, but mostly. Then we go to the next stage, and we're going to deposit and bury. So we're going to pile sediment on. Deposition, and burial. And so now we're going to have new chemical and physical conditions once that sediment is buried. And that case in Wyoming that I showed you, that's exactly what happened. That rust, iron hydroxide that formed in the soil zone, was buried, and the temperature went up because of the geothermal gradient. So the temperature went up to, it doesn't have to go up very much, maybe 50 to 80 degrees C. And you're going to start making hematite out of that iron hydroxide. And so we're making new minerals. That's where it starts in this case. Okay, so we're going to start making new minerals because as soon as we deposit it and bury it, we're going to start having new chemical and physical conditions, new solution, different kind of water that it's interacting with. So if you get down below a kilometer especially, you're really not dealing with drinkable groundwater that's in the pores of the rock. It starts to become salty, and it's reflecting interaction with the rocks themselves. So the water is changing chemistry, and you've increased the pressure, and now the temperature is going up. So you have new chemical and physical conditions. Now, if we go more than 5 kilometers, once we get down, because the geothermal gradient, let's just put that off to the side somewhere in your notes, or you can actually squeeze it in, but I already put something there. Geothermal gradient it's about, on average, 30 degrees C for every kilometer that you go down. For every kilometer. For each, God, I gotta squeeze that in there. For each, that's the shortest way I could say it. For each kilometer of burial or depth inside the earth. It's really hot inside the earth. I don't know if you've ever been there before, but the core of the earth is like the temperature of the sun. It's like 5,000 degrees C. It's really hot. And then the earth's surface is quite cool. And so the difference in between is you have a geothermal gradient. And in the crust, it's about 30 degrees C for each kilometer that you go down. Okay, so we go down, so 30 degrees C for everybody from Wisconsin and maybe even Illinois is about 86 degrees Fahrenheit. So we have to take the average temperature of the surface, and in Wisconsin, it's about 10 or 12 degrees C for the average. So our average surface temperature is about 57 to 60 degrees Fahrenheit if you took the average for the whole year. And in fact, if you took the ground temperature just below the frost line, about 5-6 feet down, it would be about 55 to 60 degrees C. Fahrenheit. 55 to 60 degrees Fahrenheit. It's not that hot, damn it. It's a comfortable temperature. In the winter, you can go in a cave in Wisconsin and just wear a sweatshirt. Like you don't need a coat. You'd be hot in a cave in Wisconsin in January. And it's cool in the summer. The temperature really doesn't change. That's the temperature of the near surface. But if we go down a kilometer, we add that, let's say 12 degrees C to 30, and now we're 42. So at 1 kilometer, the temperature of the sediment or rock is 42 degrees C. 42 degrees C is about what? 100 Fahrenheit? Something like that. It's hot. I mean, you could live there. I mean, you could live. You're not going to die, but it's hot, like a hot day in the southern US. It's hot in the summer. Okay. Now, if you go down 2 kilometers, you're going to add 30 to that. So now you're at 72 degrees C. You're approaching, at 2 kilometers, you're approaching the boiling point of water. You're getting close to it. So it gets hot. Okay. So at 5 kilometers, you're approaching 200 degrees C. And that's approximately the boundary where we go out of sedimentary systems and diagenesis or alteration, whatever you want to call it, we go to metamorphism. So it's 5 to 6 kilometers deep at about 200 degrees C. At those temperatures and pressures, clay minerals start to turn to mica. Okay, so we're making new minerals. And we're making a new crystalline texture from the new minerals forming. And we call that metamorphism and metamorphic rocks. So we leave the sedimentary realm at about 5 kilometers. Okay, other sedimentary basins with sedimentary processes that we can kind of imagine, like the Denver Basin is just east of the Rockies, and this is in Boulder County, but it's part of the Denver Basin. And you can see the mountains off to the west. They're shedding sediment through alluvial fans and onto river plains, floodplains, and it's being redistributed on the floodplains. And so that's the Denver Basin, even though there's no mountains to the east. It's kind of asymmetrical. This is a sedimentary basin in New Zealand. On the South Island, you see the Southern Alps off in the distance, and that's the Waimakariri River, the Mac, coming out of the Southern Alps and flowing across the Canterbury Plains. And this is considered, just like the Denver Basin, this is considered a sedimentary basin also. There's ocean behind us in the photo. So to the east, there's ocean, not too far away from where this photo is taken. I took this photo when we were landing in Christchurch, New Zealand. So this is just right next to Christchurch. And I actually led a field trip on this river and studying river processes for some sedimentology students, some Kiwis from New Zealand. And then another sedimentary basin, we talked about the Great Sand Dunes National Monument in Colorado. And these are big sand dunes. And the sand is trapped basically because the wind is coming from the west, from the left side of the photo. And the wind has to rise above these mountains. They're the Sangre de Cristo Mountains. The wind has to rise, and when it rises, it drops its sand. And so it's been piling up sand here for thousands, probably hundreds of thousands of years. And so they're quite impressive. But this is a sedimentary basin also. If you ever been here and driven along, it's called the San Luis Valley. And basically that valley is a sedimentary basin. Okay, are you getting bored? I think we should stop, because the next thing we're going to do is talk about controls on weathering, and maybe we do that next time.